Morning, guys. Today I'm gonna do these last four problems here, just as some application problems. These are all old AP questions. These are the types of area accumulation things and connections that you need to be making with everything going on here. First and foremost, before I start, don't forget what that command right there means. Remember, that is my That's my antiderivative command. Okay, don't forget that. And why should we not forget that? Because, we built all these accumulation functions before, and we actually drew a of x, which all the problems we did yesterday, we would actually be able to algebraically integrate and find and do all these calculations. But what do you notice on this one here? They're letting h of x equal the integral from 1 to x of f of t dt over the interval from 1 to 7. And what they're doing is they're telling us the graph of a differentiable function f on the closed interval shown above. So they're saying, hey, this is the graph of f, okay? And we do have a connection here because actually h of x is f of x is the antiderivative of h of x. So if I think of my second fundamental theorem here with this function defined as an integral, f actually equals h prime of x. Okay, they are the same thing. And that's the key to unlock this whole problem. That if I took the derivative of the function they gave me right there, okay, h prime of x actually is going to equal f with x in it. That is a ginormous connection because part A, find what h of 1 is. Well, that's pretty elementary now. That's finding h of 1. Well, we did that yesterday. That's the integral from 1 to 1 of f of t dt. That is my area accumulation line, starting line right there. What does it equal? It equals 0, okay? And find h prime of 4. Well, h prime of 4, what's that asking me? Well, h prime of 4, well, up here, I know h prime of x equals f of x, so that means h prime of 4 equals f of 4, and I know what f of 4 is. Boom, it's right there. It equals 2. So h prime of 4 equals 2. It's just the value there. Part C. On what interval or intervals is the graph of h concave upward? Justify your answer. Well, don't think of that as your nemesis. Think of that as your friend right there, okay? Because it's really important. C. I got to really break these things down a lot. Justify your answer. Well, on what interval or intervals is the graph of h concave up? So what do I think? I think h is concave up when what? When what? Well, I guess h is concave up when h double prime is positive. Okay, I'm making that connection there. Well, h is concave up when h double prime is negative. Well, they didn't give me h double prime. They gave me h. Well, if h double prime is positive, what does that mean? What's happening with h prime then? That means h prime is increasing, doesn't it? Because if I have a function that is increasing, its derivative is going to be positive. Oh, okay. So h prime is increasing. And h prime, or f, because they're one and the same up there, is increasing over the interval from what? Well, I'm increasing from 1 to 3, and again from 6 to 7. H is concave up when h double prime is positive. which implies h prime is increasing. Oh, okay, so here it is. H prime or f is increasing on the intervals from 1 to 3 and 6 to 7. And you can use open parentheses. It really doesn't matter, okay? Part C, find the value of x at which h has its minimum on the closed interval from 1 to 7. Why did I highlight closed interval? Well, because it's closed. Okay? Because it's closed, D, closed means don't forget about end points. That's what closed interval means. Not close, closed. Closed means don't forget about endpoints. Okay, well, find a minimum of what? H happens when H prime changes from what? Negative. Actually, I'm going to take this backwards a little bit. I don't want to go there yet. Okay, so a minimum of H happens when H changes from decreasing to increasing, right? Well, that means H prime changes, well, if it's decreasing, changes from negative to positive. And don't forget, H prime equals F above that key unlock things up there. So when did my derivative, when did H prime change? When did H prime change from negative to positive? Well, I can see I'm going positive to negative here. And that never happens. However, I do have endpoints, okay? So I need to know what my endpoints are. I need to know what the heck, well, I already know one of them. I need to know h of 1. Well, I know that's the integral from 1 to 1 of f of t dt. And I know that equals 0 because that was my area accumulation line. And I also need to know what h of 7 is going to be. Well, h of 7 is going to be the integral from 1 to 7 of f of t dt. And what's that going to equal? Well, I can see roughly I've got a whole bunch of positive area here, right? And I have just a little niblet of area there. Well, obviously I'm not taking away enough negative area, so I know somehow, some way, that will be some positive number. Therefore, minimum at x equals 1. Because my minimum value is going to be right there at 0. And at h of 7 is going to be some positive number because as I accumulate my area, and if you don't trust me, I'm going to accumulate my area here. And if I thought of this, okay, I'm going to say, well, I got 1, 2, 3, 4, 5, 6, and I would say if I took that one, and I put it into there, I would be about 7, and this is going to be maybe minus 1.5. I would say it's approximately 5.5-ish. I don't know what it is. It's irrelevant, but I do know it's going to be positive. Therefore, I know my minimum is going to happen when x equals 1, because that was the starting point of my accumulation line. Because the integral from 1 to 1 is 0. Okay? So, next one. What are we going to do? G. Let g be the function given by g of x equals the integral from 0 to x of f of t dt. Ooh, check it out. I have a accumulation line right here. Probably going to use that if I'm using my function described as defined as an integral. Okay? And the graph of the function f, so this is f, consists of a semicircle and 2 line segments that's shown above. Well, f equals, or g of x equals the integral of 0 to x of f of t dt. So g is the antiderivative of f, therefore f equals g prime. Okay? F equals g prime. That is the kicker to all of this. So if I got to find g of 3, well, this is going to be part A. G of 3 is going to equal my integral from 0 to 3 of f of t dt, which is going to equal that. What is that? That's a semicircle. That is 1/4 of a circle, 1/4 of pi 2 squared. Okay? And that is just that little bit minus this little bit right here, because I got to go all the way to 3. And that's going to say that's minus 1/2. Well, what is that going to give me? Well, 2 squared is 4, 1/4 of 4. That's going to give me pi minus 1/2 should be what my g of 3 equals. Okay? I used a quarter circle and a triangle to get that little bit there. All right? Well, that wasn't too bad. Find all values of x on the open interval -2 to 5 at which g has a relative maximum. Justify your answer. Again, B, if I have a maximum, means that implies, okay, g, because they're talking about g, remember, ooh, that's g. I'm looking at g prime. A maximum at g means g changed from increasing to decreasing, right? They didn't give me g, or that implies g prime changed from positive to negative. Did g prime ever change from positive to negative? Well, I can see I'm positive here, I'm negative here. Ooh, g prime changed from positive to negative at x equals 2, right? So it equals x equals 2, and then over here at 4, I went from negative to positive. That would be a minimum there. And do I need to consider my endpoints on this problem? Well, do I need to consider endpoints? Ooh, I don't know. Endpoints, open interval. No, my endpoints are open, therefore I do not consider my endpoints at all. So I have a minimum at x equals 2. My justification, I just worked it backwards, is g prime changed from positive to negative. And I can say g prime or f because they are one and the same. And that really shows them that you understand fundamental theorem number 1. Okay, part C. Write an equation for the line tangent to the graph of g at x equals 3. Well, that means we need a point at g of 3, and we need slope at g of 3, right? Or slope of g prime of 3, I should call it. Well, what's my point at 3? Well, didn't we find that in part 1? We found g of 3, comma, that was going to be, comma, pi minus 1/2. It's an ugly ordered pair, but that's okay. And what's my slope at g prime of 3? Remember, g prime of 3 equals f of 3, which equals what? F of 3 is -1. So I can say my y minus pi minus 1/2 equals my slope times x minus 3. And if I want, I can leave it just like that, or I can tweak it. Doesn't matter. I would wager to leave it just like that. So notice they're building you through. Sometimes they're having you find something so you don't have to waste a lot of time. Okay? Part D. Find the x-coordinate of each point of inflection of the graph of g on the open interval -2 to 5. Justify your answer. Now remember, points of inflection can never happen at endpoints because you don't know what the concavity is on both sides. So never consider endpoints when you are talking points of inflection. Well, let's think of this. Okay, we kind of gotta go backwards here. Come on, get out. I don't want to go backwards. I'm not going to say I got to go backwards, but D, okay, if I need a point of inflection on G, what does that mean? Okay, what does that mean? That implies that G prime or F changes from increasing to decreasing or decreasing to increasing. Right? Did that ever change? Did that ever happen up here? Did G prime ever change from increasing to decreasing or decreasing to increasing? Well, I'm increasing, then I'm decreasing. Looks like I got one right there at x equals 0. Therefore, point of inflection on G at x equals 0. And, whoop, check it out. I'm decreasing, then I'm increasing, and at x equals 3. Looks like both of those, okay? Also, what else do you notice happened at G prime at those points, okay? I could also say, or another justification, G prime has a max / min at x equals 0 and x equals 3. Therefore, point of inflection on G. Okay? Remember, if my function changes from increasing to decreasing, that's going to be a maximum or a minimum. And I'm just using my justification backwards. You always want to stop and think, okay? Find the x-coordinate of a point of inflection. Well, what happens at a point of inflection? It's on G. So I got to think about this. Okay, a point of inflection on G, that implies I have a change in concavity. How do I find that? Given G prime. Well, G prime, if that changes from increasing to decreasing, well, that shows a flattening on my first derivative, which shows a 0 for my second derivative. Okay, so point of inflection on G implies G prime is going to change from increasing to decreasing or decreasing to increasing because it's going to be a maximum or minimum on G prime at the same time. Okay, moving right along to the next one. 1999, AB5, BC5. That just means the AB and the BC test had this particular problem in common. Okay? So, what do we got? Let G equal the integral from 1 to x of f of t dt. Ooh, another function defined as an integral. The graph of f consisting of 3 line segments. You know, they're always going to give you line segments in semicircles for the most part because you can accumulate the area underneath them with a geometric formula, okay? And the graph of f is up there, and remember, G equals the antiderivative of little f. Therefore, f equals G prime, because when I come here and I use my first fundamental theorem, G prime of x equals little f with x stuck in it, okay? So they want us to compute G of 4 and G of negative 2. Well, if they want me to compute an integral, I probably better find my area accumulation line in here. There it is. So my area accumulator starts at 0. So part A is going to equal G of 4. Well, what's that going to be? That's going to be my integral from 1 to 4 of f of t dt. Well, what is that? Well, that's this trapezoid right here, which is going to be 1/2 times 1 times base 1 plus base 2 plus this guy right here. That's going to be 1/2 times 1 times 1 plus this guy here. Remember, I'm integrating to the right, which means this is going to be 1/2 times 1, my base, I'm going to say my delta x is 1, but all my heights are negative 1. So this is going to give me 5/2 plus 1/2 minus 1/2, or 5/2 is what G of 4 is going to equal when I accumulate that area. Okay? How about, what is G of negative 2? Well, that's going to equal the integral from 1 to negative 2 of f of t dt, which equals, hey, that's going to be all of this. Now notice I'm accumulating area to the left. So that's going to be a triangle at 1/2 times all my delta x's. All my delta x's are going to be negative, times all my positives is going to be 4. So it's basically 1/2, or negative 6 is what G of negative 2 is going to equal. I'm just accumulating area, but you got to keep the direction of which you're accumulating above the axis, below the axis. Delta x positive, delta x negative. What's it going to be? Okay. Now part B. Part B, find the instantaneous rate of change of G with respect to x at x equals 1. Well, there's kind of, that's just saying what the heck is G prime of 1? Well, G prime of 1 equals f of 1. They gave me the graph of f. That's why this is such an important connection. What the heck is f of 1? F of 1 equals 4. Well, therefore, G prime of 1 equals 4. Okay? Notice they didn't say justify your answer. It's an identification problem, the connection between f and G prime right there. Okay, number two, part C. Find the absolute minimum value of G on the closed, and they even did it in closed, interval 2 to 4. Justify your answer. Well, absolute minimum. This is the lowest point. So we need to find where are any and all of the minimum values happening on G. So part C, I'm going to say a minimum happens when G prime changes from negative to positive, right? So when does G prime or F, because they're one and the same, changes from negative to positive, because that would be decreasing to increasing. I went positive to negative, that's going to be a maximum right there as I switch sign, so it never happens. Never happens within negative 2 to 4. However, it's a closed interval, so I need to consider my endpoints. So I'm going to say, it's not an F though, it's G, because they're talking about G of things. So G of 4 equals 5/2. G of negative 2 equals negative 6. Therefore, absolute minimum, did they want the X value? No, they want to find the absolute minimum. G of negative 2 is negative 6. Why does that happen? I never have a change from negative to positive inside that interval, so I have no minimum in there. I only have a maximum in there, which defaults because it's a closed. I need to accumulate my area and find out what my endpoints were. And I did that in part A, so I'm using part A to answer part C. Very last one. The second derivative of G is not defined at x equals 1 and x equals 2. Well, you know why that is, don't you? You know why the second derivative, is not defined there, but it's not defined because those are corners. Those are both corners, but we're continuous, right? How many of these values are x coordinates of points of inflection on the graph of G? Well, okay, all right, well, points of inflection. I'm thinking my justify. C, D, E, A, B, C, this is D. A point of inflection happens when G changes from concave up to concave down, or concave down to concave up, right? Well, that's great. They didn't give me G. Well, what does that mean? Well, if I had a change, what does that mean? Change from concave down to concave up. That implies G prime changes from increasing to decreasing, or decreasing to increasing, doesn't it? Okay, if I change from concave up to concave down, increasing, now I'm decreasing. Decreasing, now I'm increasing. Right? What am I getting at here? Well, we're going backwards. Gotta hit pause. Okay, so as I'm cruising along and I'm just thinking about that, well, the G prime, oh, crumb. I don't want to do that. G prime is the one that they're getting me here. That's the graph I'm given. So I'm looking for when G prime changes from increasing to decreasing, or decreasing to increasing, which also implies G prime has a max / min. Now they're only asking me at 2 points, aren't they? Okay, the second derivative of G is not defined at x equals 1 and x equals 2. How many of these values are x coordinates of points of inflection on the graph of G? Well, check it out. This is G prime, and right here at 1, I can see G prime is increasing to decreasing. Therefore, I definitely have a point of inflection. Therefore, point of inflection at x equals 1. And what's happening here at 2? I'm decreasing and then I'm decreasing. I did not have a change from increasing or decreasing. Notice I also do not have a maximum or minimum. Where I do have the change, I do have a maximum. Therefore, the point of inflection is at x equals 1. Okay? G double prime is going to change from positive to negative, which it did. Okay? The slope of this line is positive. The slope of this line is negative. I had a change from positive to negative. I had a change from increasing to decreasing on G prime. Okay? The very last one. 2000. Water is pumped into an underground tank at a constant rate of 8 gallons per minute. Water leaks out of the tank at the rate of square root of t plus 1 gallons per minute, for t going from 0 to 120 minutes. At time t equals 0, the tank contains 30 gallons of water. This is an initial condition for us that we do not want to disregard. Okay? How many gallons of water leaked out of the tank from t equals 0 to t equals 3 minutes? Well, they gave me a function of the rate at which, this is the rate at which it leaks, water leaks out at that rate. Okay, so that would mean part A, how many gallons of water leaked out? Well, that would be my integral from 0 to 3 of the square root of t plus 1 dt. I'm going to accumulate my rates of leaking times minutes, and that's going to give me gallons per minute times gallons per minute times minutes equals gallons, okay? This is not a function that you know how to anti-differentiate yet, so you would type that little bugger into your calculator. We will learn how to anti-differentiate that. We need to learn how to anti-differentiate utilizing the chain rule yet, though. So, but you type that into your calculator, you're going to get 14/3 gallons. Okay? We will learn how to do that one algebraically. This would have been a non-calculator. This was a non-calculator part of the test, I do believe. But I'm not going to waste my time doing it because we haven't taught you how to do that yet. Part B. So 14/3 gallons have leaked out. How many gallons of water are in the tank at t equals 3 minutes? Well, think about this. We have water being pumped into, okay? Water is being pumped into an underground tank, and then it leaks out, and we started with 30 gallons of water. Wow, boy, there's a lot of stuff going on. Well, how much is there? Well, let's think about this. We're starting with 30 gallons of water at time t equals 0, right? It's being pumped into the tank at a constant rate of 3 gallons per minute. So, at 8 gallons per minute. So wouldn't that mean I have to add 8 gallons for 3 minutes? Because it's going to pump 24 gallons into the tank. But then I have to subtract my integral from 0 to 3 of my square root of t plus 1 dt. Well, why couldn't I just subtract 14/3 before? You can. But they want to see your calculus of the problem. I'm talking calculus right there, okay? So that's going to give me 30 plus 24 minus 14/3. Well, this is going to be gallons. This is gallons per minute times minute is gallons, minus gallons per minute times minutes gives me gallons. this is going to give me 49 1/3 gallons of water in the tank at time t equals 3. Write an expression, A of t, for the total number of gallons of water in the tank at time t. Well, wouldn't you know, we're going to have to do a little function defined as an integral here, right? At any time t, okay? So this is going to be part C. My A of t is going to equal my initial amount of water plus 8 gallons per every t minutes minus my integral from where? From 0 to t of the square root of x plus 1 dx. That is my integral. Now we're doing things a little bit differently here. Now just remember, when you're writing a function defined as an integral, the variable here needs to be different from the variable there. The variable they want you to use is time. That goes on the top of the integral. This one down here, and I need to be in variable harmony underneath there inside my integrand. I could use whatever I wanted. I could have used a y, a z, could use whatever I want, but I defaulted to x just to make that one work for us the best. Okay, and that's all we had to do. At what time t between 0 to 120 minutes is the amount of water in the tank a maximum? Justify your answer. What do they want us to find? They want us to find a maximum. How did we find those? We found those for quite a while, didn't we? And then all of a sudden we got rid of them. Maximums happen when what? A, B, C, D. Maximums happen when the derivative equals what? When the derivative equals 0. So we got to come back here to part C. We are taking our derivative with respect to t, okay? And we're going to get derivative of constant is gone. The derivative of 8t is 8 minus the derivative of the antiderivative is little f, in this case with t in it. And then what do we want to do? We want to find out, when is this equal to 0? At least I think this is going to be a non-calculator problem all the way through, because what we would do is we'd say, oh, this is tough. T minus 1 equals 8. I'm going to square both sides. T minus 1, 8 times 8 is 64. That means when t equals 65 seconds, okay, we are going to have a critical value, right? We had a critical value at t equals, wait a minute, that's supposed to be plus, plus, which means plus, which means plus, which means I just made a really stupid, God, don't make that stupid mistake. 63 is going to be my critical value. Dang it. 3, 3. Okay, so that's my 63. Remember, here is my derivative. And all I'm going to do is I'm going to come across here. And what am I going to do? I'm going to place my 63 here. I know I'm 0. And I know I'm at 120. And I'm at 0. So I can use my endpoints if I wish. They are not critical values for me. So now I need to figure out where my test points are. So I want to find out what the heck is a prime of 0. Well, that's going to give me 8 minus the square root of 1. Hey, that's going to give me 7, isn't it? That means I'm increasing there. And I'm going to find a prime of, what am I going to find over here? 63. How about I put a, I don't know, what do I want in there? I want something for a nice square root. So let's find t of 9 times 9 is what? 81. So why don't we find a of 80? because that's going to give me 8 minus the square root of 81, isn't it? That's going to give me 8 minus 9, or a -1, meaning I'm decreasing there, which means I'm showing I'm increasing, then I'm decreasing. What did I find there? I just found a maximum value. Therefore, okay, that's what they wanted, right? Now, so then I would come down and I would say, therefore, t equals 63 minutes. We'll have the max amount of water because this is where A of t changes sign from positive to negative. I might have been a little wordy there, but I also have a lot of my words buried into the justification of my work, and then that gets me to the end. I don't have to make this thing come out. I could have put 100 in there. I could have found A prime of 100, and I'm pretty sure you guys are pretty certain that this here is going to be a little bit more than 10, so it's still going to be negative. You don't have to find easy ones like you did there, but it just makes it easier sometimes. So that is where you're going to start running into functions defined as integrals on the AP test. Okay, this one they gave it, and here they made you write a function as an integral. Back here, they're giving you the graph of the function with nothing about the function. And remember, the key to unlock these problems is to know the function, the graph they're giving you, equals the derivative of the function defined as an integral. And life gets a little bit better as you move along. So, hey, thanks for playing math today. I hope you had fun, and look forward to seeing and talking to you tomorrow. Have a good rest of your day.